Is it okay now?
Yes, sir.
Okay, fine. Then we will continue our course. Yeah, we are discussing about the mathematical modeling of physical system. In that, we are now discussing about mechanical system. So, mechanical system can be modeled using three ideal elements. One is mass, the second one is spring, and the other one is damper. For a mass element, the governing equation is, if you are applying a of two types. One is translational mechanical system, right? In translational mechanical system, input is force. So that's F. Output will be linear displacement, right? Linear displacement can be denoted as X, or there will be linear velocity. That is also one of the output of the system that we can represent as V. Okay. And one more system we have. It is rotational mechanical system, right? In rotational mechanical system, input is torque and output will be angular displacement, right? Angular displacement or angular velocity. So angular displacement will be denoted as theta. Angular velocity will be denoted as omega. So that will be the difference. Okay. So again, we will continue our topic. And the next element is spring, right? The second element is spring element. The spring element is nothing but which represents the stiffness of the system, right? Where we are using spring, can you give one example? Where we are using? We are using in the see automotive suspensions, right? There we are using compressed type spring, and usually this will be the reference node, and K will be the spring constant. Okay. So if you are applying a force f of t. Similar to that, there will be a displacement x of t. So for the spring, it will be k times x of t. So this will be the relation where k is called the spring constant or stiffness of the spring. Right. That means if the value of k is high, means we need to give a high force, right, to stretch or compress the spring. Correct. Magnitude of k is high, means we have to apply greater force to compress or stretch the spring. Okay. And the third one is damper. Damper element. Damper element is, you can call it as dashpot also. Another name is dashpot. Usually we'll represent damper like this. This is this graphical representation. Is it like a piston spring arrangement? Okay. We'll denote as the constant is B. Here also let x be the displacement, f of t the force applied to the spring, damper. We can write the f of t is equal to b to d x of t divided by dt. Will be in the first order derivative. For mass, it will be in the second order. Okay. Where b is the viscous coefficient, right? Right. So this represents actually in mechanical system there is a large amount of heat is wasting, energy is wasting in the form of heat due to friction. So this element represents that part. Actually, this is a dissipative element, like in our electrical system resistance. Okay. So these are the three basic elements which are required to model a mechanical system. So suppose I have a mechanical system like this. Spring damper. I have a mass M. This is K. This is B. The displacement is X. Let f of t in the applied force. Okay. So how will you obtain the governing equation for the system? How can we write? Hello, am I audible to everyone? No response?
Yes, sir. It is a summation of all three elements, sir.
Yeah. Using the law of motion, I think you might have studied in that subject. First year one subject is engineering?
Mechanics.
Mechanics, yeah, correct. So using the law of motion, I think D'Alembert's principle. Have you heard about that? So according to D'Alembert's principle, the net force acting on the 0, right? So we can write, according to laws of motion, the given equation can be written as Fm plus Fb force due to damper plus force due to spring, which is equal to the applied force, right? So this will be the applying force, this is the opposing force. So according to Lee-Lambert's principle, we can write minus A minus B minus f of k equal to 0 under equilibrium condition. The net force acting on the system is 0, right? So if we substitute our values here, we'll get f of t is equal to m into d square x by dt square b multiplied by dx by dt plus k into x. So this is the governing equation for a spring mass damper arrangement. We can call it as mass spring damper system. For a mass spring damper system, this will be the governing equation. And what is the order of the system?
Second order.
Yeah, second order. Yeah, because the highest order of the derivative is 2. So we can call this system as a second order linear time varying or time invariant system, this one. I'll call it as a time varying, time invariant system. Why it is time invariant? When it is time invariant? If the constants m, coefficients m, b and k are constants, it is not function of time, we can call it as a linear time invariant system. The corresponding mathematical model we can call it as linear time invariant mathematical model. Okay. Suppose, see, we are using spring, right? So if you are using a spring for a long time, what will happen? Whether k will be constant? Yeah, k varies. The stiffness will vary, right? So suppose it is a time dependent parameter. So we can write the given equation as k of t into x of t. Here it is k because it is constant. Now, suppose the spring constant is varying with respect to time, we can write this k of t into time, right? So this corresponding equation, we can call it as a second order linear time variant system, because k of t is a function of time. So our output of the system will vary with respect to k of t. If all the coefficients of the system are constant, we can call it as a time invariant system. If the coefficients are varying with respect to time, we can call it as a linear time invariant system. Linear time invariant can be abbreviated as LTV. So in problem, if you are saying linear LTV system, it means that it is linear time varying. Time invariant system, we call it as LTI system. So keep in mind, okay. Okay, now we'll move to the electrical system. Suppose I have a series. So what are the elements in an electrical system?
Resistors, inductors, capacitors.
Yeah. So one type of arrangement is we can connect all the elements in series, right? Suppose I have a voltage source V, a resistance R, then an inductor and a capacitor. It will be L, C. There will be a current that is called I. The voltage across the resistance we can call it as V1. Voltage across inductor we can call it as V2. Voltage across the capacitor we can call it as V3. So according to this, if you apply Kirchhoff voltage law, we can write V is equal to V1 plus V2 plus V3, right? So V is the input, so let it be remain same V. So what is V1 with respect to I? I into R plus what about V2? Yeah, L into dI by dt plus what about V3? What about V3?
1 by C integral.
1 by C integral I dt. Okay. So what is current I? It is not just charge. So we can write I equal to dq by dt, where q is the charge. Right. So if you substitute this, you can write V is equal to, we can modify this equation, V equal to L multiplied by d square q divided by dt square plus R multiplied by dq by dt plus what about this one? Q by C. Okay, one thing, this let it be this equation number 1. Let it be equation number A. This is B, this is C. Okay. So I will write once again. It will be better. So for a mechanical system, translational mechanical system, the given equation is f of t is equal to mass into b square x by dt square plus b into dx by dt plus k into x, right? So in terms of velocity, how can we modify this equation? M into dv by dt, where v small v is the velocity, plus b plus, we can write this integral v dt, right? Okay, so you can see here one important observation. If you compare this equation, let it be this one A, this one is B, This one is C, this one is D. If you compare what is observation? On comparing A and C, you can see that there is an analogy between this mechanical system and electrical system. Right? What is the analogy? Force is analogous to voltage, right? If you compare both equation A and C, both are second order linear ODI equations. So if you compare that, you will get the force in mechanical system is analogous to voltage in electrical system, and also the mass is analogous to, yeah, correct. Yeah, mass is analogous to inductor. And what about the damper, dashport? Viscous coefficient B is analogous to resistance R in the electrical system, right? And the spring constant K is analogous to the capacitor 1 by C, right? And also velocity is analogous to, excuse me, hold just 1 minute, okay. Yeah, we'll continue. So on comparing these equations, we got force is analogous to voltage, mass is analogous to L, B is analogous to resistance, spring constant is analogous to 1 by C, and velocity is analogous to current, right? Okay. Now we have one more arrangement for the electrical circuit. What is that? Parallel combination, right? The same RLC we can connect in parallel, right? So suppose I have this resistance R, inductance L, capacitance C, and there will be a current source I, and if I am connecting all in parallel, and since it is parallel, the constant, let it be V plus or minus. So let the current flowing through the resistor is IR, current flowing through the inductor is IL, current flowing through the capacitor is IC, right? So applying Kirchhoff current law, we can write the applied current I is equal to the sum of IR plus IL plus IC. So we can write what is IR in terms of V and R.
V by R, sir.
Yeah, if V is the voltage across the resistor, we can write V divided by R plus what about IL? If V is the voltage across the inductor, what is the current flowing in the inductor? Yeah, correct. 1 by L integral V dt plus what about IC? It's nothing but sorry. Getting one call. Sorry. We will continue our course. I equal to V by R plus 1 by L into V dt plus C into
dV by dt, sir.
dV by dt. Yeah. C into dV by dt. Right. So if we rearrange the equation, we will get I equal to C into dV by dt plus V by R plus 1 by L integral V dt. Okay. And what is voltage in terms of flux? Is d psi by dt, right? The psi is the flux. So again we can write I is equal to C into d square psi by dt square plus 1 by R d psi by dt plus things instead of psi you can write d phi flux phi plus phi by L, right? So again we are having two equations, let it be, which is E and F. So if you compare these equations with the mechanical system, there also means force current analogy, right? The previous one was force voltage analogy. There is a force current analogy. That means the force in mechanical system is analogous to current. And what about the M? Mass is analogous to capacitance. And the dissipative element B is analogous to 1 by R. And again the spring constant is analogous to 1 by L. Also the flux is analogous to displacement. Right. So if we compare the two analogies, right, the previous one was force voltage analogy, right? There you can see that mass is analogous to L, right? But in the second one, mass is analogous to C, right? And also the spring constant is analogous to 1 by C. Here it is 1 by L. So from this we can understand that the mechanical elements mass and L, K are storage elements, right? Because both are analogous to either L value or C value, and in electrical system L and C are energy storage elements. So we can using this analogy we can conclude that the mass and the spring in a mechanical system is energy storage element. What about the B? I already mentioned that the energy due to friction is lost in the form of heat, and this is a dissipative element. And in the analogy also you can see that it is analog to the resistance R in electrical circuit, where R is a dissipative element only. It is not an energy storage element. So we can call B as a dissipative element. This we can call it as conservative element. Okay. Is it clear? If you have any doubt, please ask. Because now we will move to the numeric problems. Clear? Okay. So we'll move to the numeric problem. So please note down this question. I have a mechanical system. So this is the mechanical system. So this is the reference node. I have two mass elements. This is M1 and I have one more mass element. This is M2, and between the reference node and mass 1 there is a spring. Let it be K1, and here one dashboard is there. Let it be B1, and I have a spring arrangement between the mass M1 and M2. Corresponding spring constant we can call it as K12. Okay. Suppose I am having a force, applied force at mass M1, let it be F. There will be a displacement x1. Here there will be a displacement x2. So this is the mechanical system. The question is, we have to form force voltage and force current underlay. So how will you form? I have the mechanical system corresponding force voltage, force current analogy I have to apply. Right. So for that, first we have to do is, like I think you have studied node analysis, mesh analysis in electrical circuit, right? So node analysis you are doing with the help of Kirchhoff current law, and mesh analysis you are doing with the help of Kirchhoff voltage law, right? There, how you are fixing the nodes? Yeah. Yeah, correct. So like in electrical system, here we have a reference node. This is our reference node. And I'm marking this as another node, 1. This I'm marking as 2. So at node 1, how can we write the force governing equation? At the node 1. So if I, sorry? So if I draw the free body diagram at node 1, so there will be a force due to mass m1, and our force is in this direction. Let it be F. I have a displacement x1, right? An opposing force due to spring constant K1. Another one is due to dashport F1. And whether it is complete, is there any other force? See, since this K12 is a spring element which is connected in between, will be a displacement, a difference in displacement x1 and x2, x1 minus x2 acting on this K12, right? So there will be one more force due to Fk12, right? So using laws of motion, we can write F is equal to m1 into d square x1 divided by dt square plus next is force due to K1. How can we write it? Is K1 into x1, because here at the reference node the displacement is 0, right? So we can write K1 into x1. Again, force due to B1, how we can write? Is B1 into d by dt of difference in the displacement. So since it is connected between one reference node and principal node 1, so the difference between displacement is x1 minus 0, it is x1. Force due to Fk2. Fk2, how can we write? So it will be the product of spring constant and the difference in the displacement. So since K12 is connected between two principal nodes x1 and 2, and their corresponding displacement is x1 and x2, we have to take the difference x1 minus x2. So like in nodal analysis, see in mesh analysis, how you are writing, if you are writing a KVL equation in one mesh, you are giving preference to the current flowing through that mesh, right? So we have to write x1 first, then x2. So this will be the corresponding equation. So if we solve this equation, I will solve later. Let it be then that one. So if we apply the same principle in node 2, what will be the how can we write? You're understanding or not? So how will you write the node equation at node 2? Is there any applied force in that mass?
No, sir. So G equals to.
Yeah, so there is no force. F2 applied force is 0 only, but there will be some force due to F K12 alone and mass M2, right? So how can we write the governing equation? We can write 0 equal M2 multiplied by dx2 square by dt square plus K1. Now we are standing at difference in displacement will be x2 minus x1. You runs to the second one, right? So this is equation number 1. This is equation number 2. So our aim is to form the force voltage analogy as well as force current analogy, right? So now I have the equations regarding the laws of motion. So first we will derive the force voltage analogy. So in force voltage analogy, force is analogous to voltage. Mass is analogous to inductance L. Okay, fine. What about K1? Spring constant.
C1.
1 by capacitance. Okay, what about the dashpot?
Resistance.
Okay, so using this concept, how can we write our equation 1 and 2? So from 1, we can form the electrical analogues equation. So force is analog to voltage. So we can write m1 into d square x1 by dt square. That can be written as L1 into d square x1 by dt square. Displacement is analogous to, in force voltage analogy, displacement is analogous to current, right? So we can write L1 into d square, sorry, not d square. If you are writing with I, there won't be any square. If you are using charge, there will be square, right? So we'll get an equation L1 into d I1 by dt. Since we are having two displacement in mechanical system, correspondingly there will be two currents, I1 and I2, right? Plus K1 x1. K1 x1 can be written as 1 by C1 integral I1 dt plus B1 into dx1 by dt. That is nothing but R1 into I1, right? Plus K12. Sorry, here not X, it is velocity, right? So K12 can be written as instead of K12 we can write 1 by K12, right? 1 by C12 integral x1 minus x2. That means it is I1 minus I2 into dt. Right? So this will be the equation number 3. So similarly, equation 2 can be written as 0 equal to, instead of M2, we'll get L2 multiplied by dI2 by dt plus K12 can be written as 1 by C12 integral I2 minus I1 dt. Equation number 4. Right? Any doubt? Because simply you are replacing the analogous elements with electrical parameters, right? So I know the two voltage equations, equation number 3 and 4. Now I have to draw the corresponding electrical circuit. How will you draw? you can see that this is a voltage, this is another voltage, this is also a voltage, this is a voltage, this is also a voltage, right? So all voltage. So applying KVL, we can write what we can write. We can draw a voltage source in series with an inductor L1 and a capacitor C1. Again R1. Why all are in series? Because I is for L1, C1 and R1, the current flowing through the circuit is only I1, right? So since the same current I1 is flowing through all three elements, we can connect V, L1, C1, R1 and all are in series, right? Parameter C, you see. So on comparing these two voltages, we understand that there will be a difference in current I1 and I2 is flowing through the capacitor, right? So this we cannot draw in series. So let it be in parallel, that is C12. So I am closing this loop. Okay. Now this is one mesh where I1 is the current flowing through this. So if you apply Kirchhoff voltage law, you will get equation number 3. Now, how will you form the other? How will you form the equation number 4? Right? Since two currents are flowing, there will be one more branch, right? So this will be the current I2. You can see that there will be an inductor L2 and close this. Right? So this will be the current I2. So since we are having two equations, there will be two meshes. This is the first mesh. This is the second mesh. So if you apply Kirchhoff voltage law in the first mesh, you will get equation 3. If you apply Kirchhoff voltage law in mesh 2, you will get equation 4. Right? In this mesh, there is no applied voltage. So if you apply Kirchhoff voltage law directly, you can get the equation number 4. So this will be the corresponding electrical circuit of that mechanical system. Right? Any doubt? Yeah, it is easily read. So similarly, how will you draw force current analogy? In force current analogy, force is analogous to current. M is analogous to capacitance. B is analogous to 1 pi R. And K is analogous to 1 by L. Right? So if you using equation number 1, we can write I is equal to C1 into dV1 by dt. Here voltage is analogous to the velocity. So we can write V1 by R1 plus 1 by L1 integral V1 dt plus 1 by L12 integral V1 minus V2 into dt. Right? This is one equation. So another equation, how can we write? 0 equal to C2 into dV2 by dt plus 1 by L12 integral V1 minus V2. So again we are having two equations. Equation number 5, equation number 6. So what is this? This is a current. This is another current I1. This is another current I2, I3. Right. So since we are having two voltage, there will be two dots, right? We are having two voltages, V1 and V2. So just one. So we are having two nodes. This is V1. I am having one more node. That is V2. So how will you draw the cycle diagram for equation 5? Since all are currents, we can get a parallel circuit. So this will be the I which is connected to this node. And again there will be a resistance, right? So this resistance R1 and one capacitor which is also connected in parallel, right? So what about the one more is there, one inductor also will come in parallel, right? So since these first four, 1, 2, 3, these are related with node 1, it is connected to node L12, there will be difference in potential V1 and V2. So where we want to connect that inductance, the inductor should lies between V1 and V2. That is L1, 2. So we have completed the first part. So what about the second part? For equation 6. Anyway, this we already got. We connected in between 1 and 2. And there will be a capacitor C2 with respect to 0. So this will be our reference node. So the right. So this will be the force, current, analogy, electrical circuit. So if you know the mechanical system, using this concept, we can draw the corresponding electrical circuit. If you know the electrical circuit, you can write the corresponding mechanical system also. Okay. So if you have any doubt, please ask. Yeah. See, this one is for a translational system, right? Suppose translational system, instead of force, torque will come into the picture. Yeah, system. It depends upon the which type of system, mechanical system. And another important thing is, if you are this M represents for a translational system, right? If it is a rotational system, how will you represent mass?
Inertia, sir.
Inertia. So we have to use the term J. J will be moment of inertia, right? That will be the difference. Other than that, nothing will be there. And B, in both cases, it is B only. K also B only. The only thing is, instead of X, theta will come into picture. Instead of velocity, linear velocity, angular velocity come into picture. That's all. That is only difference. Remaining all do one problem for rotational system also in the coming class. Okay, by the time you know. So other than that, everything is fine, right? So using this, okay, so there is the final conclusion is this. There will be an analogy between. You have studied D'Alembert's principle. This principle is related with laws of motion, right? So this law is having an analogy with what? Kirchhoff voltage law as well as Kirchhoff current law. Okay, fine. So in using D-element principle, we can tell the net force acting on a system is zero. What is Kirchhoff voltage law? The net voltage in a loop is zero, and the net current acting on a node is zero. Okay, so there is some analogy between voltage and mechanical system and electrical system. Okay, clear? Okay. Okay, then we'll stop.